Hi and welcome to John's Maths Book. In this video, we'll be exploring another key concept in mathematics. If you find this tutorial helpful, then please show your support by subscribing, liking, and leaving a comment. Your positive engagement helps me create more content and allows me to bring you more valuable maths lessons. Without further ado, let's go over to the whiteboard. Let's use triple integrals and cylindrical coordinates to find the volume of a sphere. I appreciate there are other simpler ways of doing this, like using the formula for the volume of a sphere. However, this example serves to demonstrate the technique and steps of using cylindrical coordinates and triple integration. For more complicated examples, you'll need to use these techniques as there'll be no simple formula. In this example, the sphere has an equation z squared equals 16 minus x squared plus y squared in Cartesian form and has symmetry about the x, y and z axis. Let's take a look at the sphere in 3D form using a graphing tool. So this is the sphere and we're going to find its volume. As you can see, it's symmetrical about the x, y and z axis. Our first step in the process is to convert the Cartesian equation of the sphere into cylindrical coordinates. So we need to convert x, y and z to r, theta and z in the equation that describes our sphere, which is z squared equals 16 minus into the bracket of x squared plus y squared. To do this, we need to substitute r cos theta for x, r sin theta for y, and z remains the same, so z equals z. After making the substitution, we get z squared is equal to 16 minus r squared into the bracket of cos squared theta plus sin squared theta. And using the trig identity, where cos squared theta plus sin squared theta equals 1, we're left with z squared is equal to 16 minus r squared. And therefore z is equal to plus or minus the square root of 16 minus r squared. To find the volume, we need to integrate over the region E and some infinitesimally small pieces of volume shown here as dV. We need to unpack this and define the region using cylindrical coordinates. This will give us our limit of integration for r, theta and z, and then look at what dV equates to in this context. So let's start with the limits of integration along the z-axis. The best way to think about this is that we're summing infinitesimally small pieces of volume along the z-axis between a function that defines the upper hemisphere and one that defines the lower hemisphere of our sphere. In this case, the function defining the upper hemisphere is z equals the square root of 16 minus r squared, and the function defining the lower hemisphere is z equals minus the square root of 16 minus r squared. The upper hemisphere is above the xy plane and the lower hemisphere is below the xy plane. So the upper limit of integration for z is the equation of the upper hemisphere, where z is equal to the square root of 16 minus r squared, and the lower limit is the equation of the lower hemisphere, where z is equal to minus the square root of 16 minus r squared. If you remember when we looked at volumes using polar coordinates, we multiplied by a height component, which was the difference between the upper function and the lower function. Well, this is essentially the same, except we are now using an integral to do this. So now moving on to the limits of integration for r. If we look down from the z-axis, we see that a shadow in the shape of a circle centered at 0 is cast on the xy plane. The upper and lower limits of r will be along the radius of the circle, where we'll sum infinitesimally small pieces of volume. The upper bounds of r is where our two hemispheres intersect, and that's where the equation of the upper hemisphere equals the equation of the lower hemisphere. So where the square root of 16 minus r squared is equal to minus the square root of 16 minus r squared. And so solving this equation for r, we can add the square root of 16 minus r squared to both sides of the equation to give 2 multiplied by the square root of 16 minus r squared equals 0. And dividing both sides of the equation by 2, we get the square root of 16 minus r squared equals 0. Squaring both sides of the equation gives 16 minus r squared equals 0. And this leaves r squared is equal to 16. And taking the positive square root of both sides of the equation, we're left with r is equal to 4. And this forms the upper limit of integration. And r begins at the origin of the circle, so where r equals 0, and this forms the lower limit of integration for r. And to find the limits of integration for theta, we need to look at the coverage of r as it rotates anti-clockwise around the circle. As we can see, r goes full circle and therefore rotates the full 2 pi radians or 360 degrees. So the lower limit of theta, where theta starts, is at 0, and the upper limit of integration is where theta finishes, and in this case it's at 2 pi radians. So we've now defined our region using the limits of integration. Let's now unpack what we are integrating. So in our case it's dv. So dv represents infinitesimally small pieces of volume. We're using triple integrals to sum each of these to get the total volume. Let's look at the dimensions of one of these. If we look at the green shaded region, this represents an infinitesimally small piece of volume dv. We can think of this as a tiny rectangular box where the volume is given by the height multiplied by the width multiplied by the length. So let's apply this to the green shaded region. We can see that the height is along the z-axis, and it's an infinitesimally small piece of z represented by dz. The width of the box lies along the radial distance r and is an infinitesimally small piece of r represented by dr. And the length lies along the arc of the circle and is infinitesimally small. Now the arc length of a circle is given by the radius multiplied by the central angle theta. In this case, theta is infinitesimally small, represented by d theta. If we now put all these infinitesimally small dimensions together, we see that the volume dv is given by dz rdr d theta. And we sum all these pieces of volume using our triple integrals to get the total volume. So now we have our triple integral where we're integrating dz rdr d theta. So let's begin the evaluation process, starting with the inner integral. So we want to evaluate the integral where z equals minus the square root of 16 minus r squared to where z equals the square root of 16 minus r squared of dz. Using the power rule, this evaluates to z. And plugging in the limits of integration, we have the square root of 16 minus r squared minus minus, which becomes a plus, the square root of 16 minus r squared. So this gives 2 multiplied by the square root of 16 minus r squared. And moving on to the middle integral, we want to integrate from r equals 0 to r equals 4 to r multiplied by the square root of 16 minus r squared dr. To evaluate this, we're going to make a substitution. So we're going to let u equal 16 minus r squared. So du is equal to minus 2r dr, and it follows therefore that minus du divided by 2r is equal to dr. So now making the substitution for 16 minus r squared and dr, we have minus the integral of u to the power of a half du. And evaluating this using the power rule, we have minus 2/3 u to the power of 3 over 2 plus a constant of integration c. And now substituting back in for u, we have minus 2/3 into the bracket of 16 minus r squared to the power of 3 over 2. And we need to evaluate this between 0 and 4. And if we plug in the upper limit of 4, we get 0. And plugging in the lower limit of 0 gives 2/3 multiplied by 16 to the power of 3 over 2, which equals 128 divided by 3. So now moving on to our outer integral, we want to integrate from theta equals 0 to theta equals 2 pi. 128 divided by 3 d theta. And using the power rule to evaluate this, we get 128 divided by 3 multiplied by theta. And plugging in our upper and lower limits of integration, we have 256 pi divided by 3 minus 0, which gives us the volume of our sphere, which is 256 pi divided by 3.